Grebe Bio actually is a tech bio company. We are using AI, we use big data analysis and even the automation to integrate into bioprocessing. In the last few BPI conferences in the West Coast and even last year, I present a few platforms, cell line, media. But today, I would like to present called ecosystem. This intelligent ecosystem actually combine all the different platforms together, covering from drug discovery all the way to the CMC part. So it's kind of like a complicated process, but if you follow my direction, if you look at the 12 o'clock, the blue parts, we are using big data analysis to figure out what kind of a target is hot in the future. Also, if you look at the red part, the yellow part in the 2 o'clock of our body, we are using in silico to generate antibody sequence instead of using a wet lab like a phage display or use the mouse immunization to get a sequence. Once we get a sequence, in the green part is alpha DEX, we can optimize the molecule design, humanization, affinity and maturation, and developability. Then we confirm with the in vitro study, in vivo studies, get a PCC, then we went into the CMC part. So if you look at the red part, alpha cell, we can use the site-specific integration platform to get a high titer, stable cell line. And also the purple part is also mixed with the culture media with this cell line. So these are all different platforms. When we spread into all those drug development process, you can see all those key platforms, sequence generation, in vitro study, even the cell line development, media development, all those platforms, we can improve those efficiency. So the take-home message today is in the Grebe Bio, we're using different technology to try to speed up the process to help drug developer get their results as quick as possible. So even we use this ecosystem into this drug development platform. So as you can see, normally starting from scratch, you get a target, you get a PCC, you got an IND filing, normally take at least 2 years. Usually it takes about 2.5 years under 3 years. By using this ecosystem, as you can see, every part can be shrink down to the reduced time. So if you look at the green part is drug discovery, it's reduced time. If the blue part is a CMC, also reduced time. So at least by this drug development, we can save at least about 1 year, over 1 year time frame. So by this kind of the application, it's very useful for the drug developer to speed up their product to go to the market. So as you can see, it's a very complicated process. So today I would like to start with cell line development. So we present this what we call site-specific integration platform for cell line development, or called alpha cell. So as you know, in the traditional process, we usually it's random insertion. Everybody knows that. So as you can see, the cell pool is unpredictable. It's mixed. Some is stable, some is unstable. So you have to spend a lot of time to do the screening to get a monoclone. Once you get a monoclone, you still take another 3 months to do the stability evaluation. So at least you need to take 6 months to get your high titer stable cell line. But if we use this, our alpha cell, just take about 1.5 months, you can get what you want. So first of all, we use AI trying to find those hotspots in the genome and labeled with the green protein. Then we use the GOI to do the homologous transfection. You can express your protein in the same place. So it ends up your cell pool is a uniform cell pool. So with this uniform cell pool, you can do a lot of things very easily. So you just need 1 or 2 places to get a single cloning. And then the site has been pre-selected as stable. So you don't necessarily waiting for your stability results to move forward. You can move, once you get a cell clone, you can go down to the downstream. So you don't have to do the stability evaluation. Of course, for your filing, you have to do this in the other time, but it's not becoming your bottleneck anymore. Secondly, the other things you can make some materials from the cell pool for the tox study, if you're in the emergency like a COVID-19, and also you can make predicted product quality. So with this uniform cell pool, we can do a lot of things by this technology. So the first question I think that most of people will think they ask is how accurate your AI to find those hotspot, which is high titer. So this slide just showing that these slides, every dot represents a cell, one cell. We use the green protein to express in the cell. So the y-axis represent fluorescent intensity to represent the titer. So as you can see, all those circled cells is being predicted by the algorithm, by our AI algorithm. So as you can see, all those selected cells is in the high titer in the whole population. This slide just showing that the standard process is a high titer, is a stable. So if you look at the left chart, we make like almost 100 cases orders. So the average, the median expression level is 6 grams per liter. And some of them, for example, the top square is 15 grams per liter. This is one of our customers, they filed IND already. So in the 500 liter scales, they're making 15 grams per liter. The second one is a nanobody. As you know, most of the time, the nanobody is very hard to express. So we're making 13 grams per liter. And also for the bispecific is another headache for the titer. So we end up in the 4-chain bispecific product is 8.3 grams per liter. So as you can see, with this selection, we select the high titer and the stable cell line. Most of the time, you can make a relative higher expression level. The right chart just showing that how stable the product is. So since we select this site is stable, so we transfect 8 products into the platform and isolate the single cell, become a monoclone, and then we do the 3 months like a standard 3 months stability evaluation. As you can see, all those expression level is plus minus 20% variation is acceptable for the stability evaluation. So the first advantage besides the titer and the stability is fast. And since we labeled with the fluorescent in the site, so our host cell is a green protein. So if you look at the left one, is a host cell is green color. Then once we transfect the GOI, we mix, when we get a cell pool, is fluorescent with the non-fluorescent. We use the homologous transfection to replace those GFP so they become non-fluorescent. Now after step 2, so you use a very simple cell sorting equipment, fax, Satina, even VIPS. You can easily to pick those non-fluorescent, which is positive cells, into the 96 well. So you just need 1 plate or 2 plates is enough, way enough to get what your product. Then after that, 24 plates, 6 well plates, and shake flask. So normally after transfection, after 1.5 months later, you can get your monoclone. In the meantime, once you collect those positive cells, you still have a lot of positive cells left in the cells. So you can collect all those positive cells into the one vessel, become a cell pool. Then you use the fed batch to make some materials to do some quality evaluation, even make some materials for your early study or even some downstream work. So in this case, the process from the 6 months of traditional process become a 1.5 months faster process. So this give CLD people that is a very faster time to get your cell line. Based on this one, as you know, everybody, the traditional process is a long chain processing. You get your cell line, they get a stability, then you evaluate your product quality purification. Normally it takes 16 months, plus minus. But since our cell pool is the uniform, so a lot of work in the later stage can be parallelly to working in the same time. So that all the process only for R&D, for the CMC parts, we can save at least 6 months. Okay, so this cell pool is become a predictable model. You can predict your titer in the cell pool. You can predict your product quality. You can predict your other parameters. So this gives us a lot of benefit for the CLD people that you can save a lot of time during the R&D filing. The second advantage is in the early stage, in the cell pool stage, you can do product evaluation, product quality evaluation for the biospecific and also ADC. As you know, in the biospecific, it's relatively hard compared to the monoclonal antibody. So one is a relatively low titer, and also sometimes have a higher missing pairing percentage. So this is our summary showing that with our platform, we use to make different kinds of biospecific antibodies. Some is 2 chains, some is symmetric, some is asymmetric, some is 3 chains, some 4 chains, even nanobody. So as you can see, the titer is relatively high, 8 gram, 10 gram, even 12 grams. And even for the correct pairing, we can make over 80% correct pairing. So with this platform, we can solve these 2 pain points in the biospecific field, low titer and low correct pairing. Why we can do that? So in this platform, we design a vector. They have 4 open reading frames. So we find out with our experience, those heavy chain and light chain with different position can give different titer level and also different correct pairing percentage. So as you can see, with these reading frames, with the heavy chain, light chain with different position, you can have different results. So first of all, we make all different kinds of the combination. Then we screen with the transient expression to make sure they can be expressed. After expression, then we use the homologous transfection to make a different kind of cell pool. Each cell pool has one combination of the arrangement. Then you can make a fed batch, make some materials to do the quality evaluation. For example, titer, or even this correct pairing. Once you find one of the combination is the best, then you can use this cell pool move forward to get the single cell cloning. But the rest of it, you don't have to do the next steps, so that you can save a lot of time for the drug developer. So this is the first, the one benefit for the biospecific evaluation. Another one is for the ADC. As you know, ADC is a drug with the chemical drug with the antibodies. So if we use the traditional process, you have to do all those monoclone, get the RCB, get the materials, and then you have to work with the chemicals to find out the optimization of linkers or the drug load. But with this uniformed cell pool, you can quickly make a protein. Then you can start play with this chemistries to find out which is the best optimized linker or the payload. By the time when you finish your RCB, get the materials, all your chemistry optimization has been done. So you can save a lot of time. This is another benefit for the ADC. So this is an example. We use the 4-chain bispecific antibody as an example. So as you can see, there's a different kinds of arrangement, position of the heavy chain and the light chain. And the correct pairing shows 87%. But if you use a different combination, become 29%. So as you can see, the position of the light chain and the heavy chain in the different places can give you different correct pairing. Same thing for the titer. you can see with a different position, some is 6 grams per liter, sometimes it gives you only 3 grams per liter. So the position also can cause the different type expression level. So this is the example showing that with this vector, which is a fit with our platform, is a 4 open reading frames, can make a lot of difference. So besides this technology, a lot of questions regarding the regulatory. So since we are using green protein, we're using integrase, people say, do you have a contamination in the final products? So we do all this assays show with a whole genome sequence or PCR showing that in the final products, we don't have GIP gene. Theoretically, shouldn't be, right? Because our GOI will replace the GIP. Second one is the integrase. We're showing there's nothing left in the final product. So with this our platform, we have a customer already filed IND, used our technology, filed IND in the US and also in China for the product. Besides this CMC cell line development, this cell system can be used in a drug discovery. So the first one, as you can see, we can use it for saturation mutagenesis. The regular saturation mutagenesis is a random one. So it takes a lot of time, 1 round, 2 round, 3, and usually take 3 or 4 months. But with our platform, since it is a site-specific, so once you have a whole bunch of the mutation, use the homologous transfection, each cell has 1 mutation, 1 site. So after 7 days, you can use the FACS to make a screening, see which one is positive, which one you want. Then you just do the genome sequence. You can find out which mutation is best for your affinity maturation. So this is another application in the drug discovery with our platform. Another one is for transient. I think last talks, they are talking about also, we find a lot of headaches in the drug discovery is we use HEC 293, we use the QS. Those product quality is sometimes different from the final product. It's those kind of headaches getting more and more show up in the industry. So what we do is during our processing to make our RCB, we can use this cell for the transient. So within 7 days, use the cell pool, we can make materials. This materials quality is the same as the single cells product quality. So in this case, the early stage development people get product is the same as the final product. So the next slide just show one of example for the charge variations. So as you can see, in the top one, we use the QS as a transient. The chart showing that is about 41% is a neutral peak, which is pretty unhappy about number. But if we use our alpha cell for the transient and also for the stable cell line, they have the similar percentage of the neutral peak. So this slide just showing that if you use the same cell line in the drug discovery and with the CLD development, you can get you have a good quality and in the before and afterwards. So the take-home message is with this single site-specific cell line, we have 3 functions. Either one can do the CLD for the stable cell line development. Also, we can do the transient expression. Also, we can use for affinity maturation with the saturation mutagenesis. So there's 3 functions with 1 cell line. So once we get this cell line, media is also important. So we have a new technology. It's different from traditional process. Usually for the traditional process is screening, take 6-9 months to get your product. What we do here is we don't do the screening. So you use one media and test it. If it doesn't work very well, you take the supernatant, and we can measure those supernatant of those consumption of the components of each media. And our AI can figure out what kind of components need to be added, what kind of a component need to be removed, so that you get the supplement and back to the original media, do it one more time, you can get the good results. So it's very simple, no screening process anymore, just do a couple of time experiment. So this slide is very showing that if you test it, one of our catalog media, you take the supernatant by the end of the processing. With the OPA, we are showing that, sometimes, for example, this red bar showing this component has been totally consumed, so we need to add. But if you like, this green part is less consumed and some is generated. So we need to remove these components in a certain way so that we can get the supplement and back to the original and do the one more experiment. So this data just showing that with this faster way, we can improve this titer, sometimes 4 to 7 grams, sometimes 6 to 3 to 7 grams sometimes a significant improvement. With this cell line, with this media, sometimes still cannot get good results. Sometimes still low titer, sometimes always get a precipitation. So we expand our capability, use the AI technology for the drug development. So this slide is just showing that we can use AI to predict this sequence is good or bad. Today, I just want to focus on the two things which is related to our CMC parts. One is aggregation and solubility prediction. Our accuracy right now is about 79 to 100%. The second one is we can, based on sequence, molecule sequence, to see if it's a high titer or it's low titer relatively. So this slide is just showing that aggregation. We use the threshold, which is we use a number like 1. If it's above 1, showing that it's have a precipitation possibility. Those wet lab showing that it's really see the crowdness, okay? And if it's lower 1, it's a soluble, and I can see the accuracy is roughly about 79%. Most of it is soluble. So based on this sequence, we can predict your formulation, your DNA sequence, if it is possible to make a precipitation or it's a soluble. If it's possible to make a aggregation, we can optimize it to modify it to solve this problem. Another one is very exciting things is we can, based on this molecule sequence, can predict if it is a high titer, is low titer. So we use our particle data to make AI training to showing that which sequence can be low titer, can be high titer. Then we use this algorithm to predict our real results, showing that some we can predict, this red one showing is incorrect, but most of them showing that is a high, if it predicts a high titer, it's above 4 grams per liter. The interesting thing, this green one, which I'll show the case study, this is the only one we have for the forwarding prediction. It means without knowing the titer yet, AI to predict it's a high titer. So 2 days ago, the data just shown this product is 7.1 grams per liter. So this is very, very interesting that with used DNA sequence, probably we can give a good, to predict if it's good data, high titer or low titer. Since the time is very, very short, so I'll give you a very quick case study. This active B is one of the target is very hot right now. As you know, everybody talking about the weight loss drug, right, GLP-1. But I think one of the headache is they lose weight, but also lose the muscle. So this target is just showing that we can increase muscle, keep the muscle, and also lose the weight. So this is a very new target. So with our platform, so we can use the in silico method to create the sequence without animal screening. Then we use AI to figure out this humanization, affinity, and developability, and do the in vitro study and the in vivo study. So all those prep process only take about 7 to 9 months to get a PCC. So once you get a preclinical assets, you have a lot of business model. You can license out, or you can do by yourself, or you can do a lot of things. Within I think we're missing. We're missing one slide for some reason. So within 5 months, we can get the sequence, the affinity starting from nanomolar level to the picomolar level. So the affinity is increased by 100 times. Secondly, we got the EC50, which is efficacy comparing to the original is the same level. And finally, we used within 1.5 months, we get this product cell line, the stable cell line, 7.1 gram per liter. So very short time can help to get the PCC. So this slide just concludes that in the whole drug development, drug discovery with the CMC, all those red spots showing that we use AI technology to improve the process, to help drug developer to speed up, to save time. Those yellow one is ongoing process. We are trying to use AI technology in the purification, to use a small scale to predict how do you do it in the large scale for the purification. So, this is I'm sorry, I think some reason make a wrong one. So as you can see, this is a data showing that our affinity within a couple of months, we can increase by 100 times. And EC50 showing that is the same as the original drug. And also this just showing this developability. Aggregation is no problem. The binding affinity is no problem. Homogenization has no problem. Finally, the CMC cell line is 7 gram per liter. Okay. So I think it's a very short time to present so much things to complicate it. So in case you guys have a question, we have a booth in the 1138, or you can scan my barcode and you can contact me for the future questions. Any questions? Thank you.
Thank you, Michael. I love it. Weight loss, muscle mass increase, and then how about the male pattern balding?
We're trying to do that.
Do we have any questions for Michael?
Yeah, so Michael, very nice talk and nice work, by the way. So my question is specific to the process development and control of the product quality. You have done the media characterization and AI. How much work is you are planning to do connecting the process development to control the product quality and which eventually control the clinical efficacy?
For clinical tests, I don't have a plan yet. It's a lot of work. So that if you focus on the preclinical, it's a lot of work to do. I think the take-home message right now is right now, a lot of people trying to make AI too fancy. Everything is smarter than people. I don't think at this moment AI can do that to beyond human intelligence. But one thing we can do, definitely can do, and also we already show that, is faster. So every time, if you 6 months, we can make it 1.5 months. If you have 1 year, we can make it 6 months. So faster, I think, is the most important for the drug developer, even for the patient as well.
Really nice talk, thank you very much. Also very impressive titers that you show in terms of productivity. I was just wondering, what process conditions do you use? Like, what is the starting density of the cells? And
it's a regular. Right now it's a shake flask scale. I believe it's 500,000 cell density to start with. 14 days, and probably reduce temperature at day 3 or day 4.
Okay.
Yeah, it's a regular process.
Well, let's go into the next question. Quick question. So I'm no AI expert, but I had heard that garbage in, garbage out, and so it's really the training data sets that are so critical. Amazing results. How, without spilling your IP, how do you do that?
Yeah, 2 things. Number one, all those data, most of data is our in-house data. We have to we established our company 5 years ago. So the first 4 years basically is making in-house data. You cannot find data in public. So number one. Number two is even garbage in, garbage out, we still have to make data. For example, the cell line. We use the cell morphology. The reason why we can find this hotspot is based on the cell morphology. A lot of research is showing that the cell morphology is related to the protein synthesis amount. So we make millions, or so far we already make 100 million cell images in-house to do the AI training. Same thing for the formulation. We started with 600 formulation. Right now we have 10,000 formulation in-house, about 1 million data points, like cell density, titer, viability, everything. So nothing you can do about it. You have to do the in-house. And also this is a barrier. So this is all in-house. You cannot find it. So anybody, competitor want to get in, you still need to spend 4 years, 5 years to get your own data. You cannot find it somewhere else.
So just to follow up on that question, you were showing predictions on titer, but you're also, modifying your vectors and modifying your media. So if your media package is, giving you a delta of, 20, 30% there, it seems like that would confound the data set. So how do you do that adjustment, whatever
for the
that would
media
call it?
improvement, right?
No, I mean, so you said, we can predict high and low just based on sequence, and then I'm thinking, and then you give me a target of what that is, and I'm thinking, well, because like you said, you have to have a lot of data in there, and if you're doing continuous media production improvement for different assets, I'm just getting confused, or I'm trying to understand how you...
True. So when we predict the titer, we are talking about it by nature. So without any further optimization, just naturally, so you use a very simple commercial media, you can make whatever the titer is. Of course, in the downstream wise, you use change media to do all different things is another story. We are talking about if this sequence can easily make a high titer, of course, with further improvement, it get even better. If it's like 1 gram to gram, 1 or 2 grams per liter, there's no way you can make a 10 grams per liter by media development. So we want to solve this problem in the early stage. Just like a baby, if you born strong, beautiful, and of course when you grow up, everything's easy. If it's weak, you have to take a lot of efforts to raise the baby, something like that.
Thank you for your talk. And I have a question about the alpha cell.
Oh, hold on.
I have a couple of questions about alpha cells and alpha DAGs as well.
Okay.
So I've seen this 6 grams per liter, so the median titer with your alpha cell, and I am wondering how many copy numbers of landing pads were integrated in these cells.
So it's a more detailed thing. So when we select this the hot spot, first of all, we randomly to insert this green protein into the genome. So once we select this high titer, we have to narrow down because we have a million cell, everything is good. Then narrow down like one site and 1 copy number, and easy to grow, easy to transfect. So all these kind of different parameters, we are going all the way down to probably ends up, we screen like 100 million cells, cell pool, ends up like 3 or 4 cell line. It has a good one. Yeah.
My second question.
The answer question is 1 site, 1 copy, yes.
Then is the productivity was the only parameter for the selecting hotspot? So we use this as first selection, the hotspot, the high titer. For the quality wise, we have to use the regular way yet. Yeah. And my last question is about alpha DAGs. And you showed more than 80% of predictivity for the high or like relative titer,
Yeah.
like high or low.
Uh-huh.
And I was just wondering how big the data sets were used for this algorithm training.
This data is from public, so the people that use the tonight, I think it's 2,000 something.
2,000.
2,000 data points. Yeah.
Thank you.
Data set. Yes.
So it's my turn. So I have a question about the bispecific construct. When you change the position of the chain, you have 4 chains, right? 2 heavy chains, 2 light chains. When you change the position, the productivity changed. So product quality changed. So my question is, when you change the position, is each change expression level changed?
The level, the expression level.
Yes, when you switch. Yeah.
So the actually in the last in the BPI West, I believe MG and somebody, everybody understand that the position, even the monoclonal antibody, the heavy chain, light chain with different position, give you different expression level. Even with four chains, so we show this data as well. If you have a different position, it gives a different expression.
So next question is, do you use the same like enhancers for each chain?
Yes, we use every reading frame, we use an individual promoter.
So they're different?
This is different, yeah.
Oh, okay.
Yeah.
So that means you can change the enhancer activity for each chain. You don't need to switch the position. Is that possible?
We haven't tried that yet.
So because each change expression level is different in each position, then you can change the expression level.
Expression level.
You don't need to
we
change
use the
position.
same promoter for each reading frame. But once you find the position different, even though second place to third place is totally different.
Okay.
Yeah,
Thank you.
this is our experience. Yes.
So thank you very much for the presentation. My question is that if I pick a random clone to establish the MCB after the transfection, how many percentage of the clone will prove to be stable eventually? So I just try to understand the risk.
The stable?
Stable.
With our experience, it's almost 100%. So this site, the hotspot, during our screening, we make sure this hotspot is stable. Okay, then theoretically should be stable, right? So we show the data. We infect 8 products and get a single cloning. Then we do the 3 months passage, shows is a stable for the expression level. Also genetically, we test those the site. Genetically, it's stable because of one site. It's easy to do that. Yeah.
Okay, great. Thank you.
Yeah.
Yes. Follow-up question. So you identified these hotspots, which is really interesting, and also good to see that they're stable. The first question: how many of those? I think that was.
It's one site. So sometimes you have 2 sites, 3 sites. Even when we find 8 sites, it's useless to us because it's very hard to control. So we just specifically to narrow down to one site. So there's get high expression. So all the data we show here is only one site. We use
one site in the entire genome.
Yeah.
Okay.
Yeah.
And so the way that you get the genes, as you showed, you get them in is just by homologous recombination, or do you use transposon-mediated integration?
We don't use a transport, just a homologous transfection. So we use it, 2 arms with this GFP. Then in the vector, you have 2 arms with your GOI, and they just cross to replace the whole gene, the GFP out of the genome.
And you screen for the absence of GFP
yeah,
expression.
So in the beginning, it's a green protein, is a color, right? So once you replace it, become non-fluorescent, it's a non-color. So you have a color differentiation. So easily use the FAX or Satina, everything easily to pick those non-fluorescent. It's become positive one. So you just need 1 or 2 96 well place. You can make everything is positive.
So basically, you will always have just one copy of the gene of interest.
Yeah.
And that gives you these huge expression levels.
Yeah. So that's the beauty of the AI. In the genome, definitely you have someone can make a high titer, but you don't know which one. So for the random one, sometimes you can find it, sometimes you cannot find it. For this one, we just accurately find the site and label it with the green protein.
I think this really proves the fact that it is not about the number of copies that you have in the genome, which of course was always the dogma in the cell line development world.
But GS knockout is a multi-sites. They use the multi-sites to make a height. This one is one site make this tighter.
Very nice, thank you.
Thank you. I'm sorry.
For single cell cloning, you only have to do few of the single cells. Because
normally theoretically, by one place is enough.
Okay.
But people say, I will make 2 plates. So 2 plates, they have nothing to do, right? So they want to make sure they are busy. So 2 plates ends up like a 200 clone to start with a 50% survival rate. You still way enough clone to play with.
So do you get a variation? I'm assuming no variation between the clones because they have like...
We do see variation. Theoretically, supposedly everything's the same, right?
Yeah.
But for some reason, maybe I think the electroporation shocked the cells. So some reason, still see some variation. But usually, with our experience, like top 100, top 10, top 20, is variation very low, but we do see some is very, very bad.
So variation would be like plus minus 10%, or you see more than?
Yeah.
Okay.
Mm-hmm. Yeah.
Can I ask an additional question? So have you checked the copy number of the GOI after you...
Copy number?
Yeah, not the GFP, but the GOI, because I thought that there's a possibility that because you are using the homologous recombination, the other copies could be integrated as well.
We do use the whole genome sequence to show that it's only one site. I think your question behind is, do you have a random insertion, right? We don't see anything like that. Yeah.
And we can keep the questions going. I just want to let people know we're about 10 minutes into a break, and we're going to need to start back up again in 15 minutes. So we can keep the questions going, but if anybody needs to take a break or anything.
Okay. Yeah, can I ask one more question? How many hotspots have you characterized? So
3, 4. So far we have 4 and 5. We use only 1 to do all those work. Yes.
So have you characterize the molecular characteristics
we find location. And find IP as well.
So my question is, can you compare those sites and use AI to maybe predict a better one?
You need a lot of data because right now it's just only 5 cell lines. How can you make AI training to do that? You cannot. I don't think so. Even you can use AI to predict, which site is the hotspot. You cannot knock in unless you have to use the CRISPR-Cas9. So you have to use the random process to spread this site. The GAP into the different sites. You find the spot and then label it.
Could you use transposons to put other sites in?
Random. We use a random insertion first.
Okay.
Yeah. Mm-hmm.